My name is Stephen Alonso, and I'm a flat earth scientist. I'm pushing the boundaries of where modern science has failed. I'm going where no one else before me has gone.
Hello, it's Steve from Flat Earth University, and I'm here with the final experiment challenge number 1. I think I'm the first submission from possibly both the flat earth and the globe sides. That's a very exciting thing. What we're presenting here is a flat earth distance formula. Now, even though me personally, I believe that the Haversine formula is a 2D unit circle flat earth formula and that globe has took it over, I can still accept the premise of Will's challenge and create a flat earth formula based on the known concepts we have, such as the fluid ether, the Lorentz length contractions, the height of the firmament. And we end up with the formula right at the top, which is based on flat earth concepts, and most importantly, there is no spherical trigonometry in that top formula. And that's the whole point. Can we do it without the Haversine? And what I ended up finding was not only was the differences very small over those long distance flights. If you haven't watched Will's video, I encourage you to do it so you can see the 4 test cases that we had to match up against. And based on these error margins, what I ended up finding out is that my formula is actually more accurate than the globe formula. Now, there could be 2 reasons for that. In globe theory, well, I guess in heliocentric theory, you have to deny ether. If you believe in spherical geocentric cosmology, you would accept the fluid ether. You don't have to deny science too much. So I don't know if in globe theory this has been ignoring how to correctly measure length contractions as we travel through latitudes. Another major issue with the globe theory is that it seems derived upon the flat earth formula. You have to first wrap it around a ball, and that's why you end up with these errors. Let me go to right here where we actually then tested the 4 test cases. We see the Haversine formula, but then we also see the flat earth formula, and we see how close it is, and we see those, it's less than 1%, it's like 0.2%, 0.1 in many cases. We see that. So how I was able to conclude, and you see all the math here, you can go through the math yourself. For example, for Los Angeles, we show you the Haversine formula, then we show you the flat earth formula. So you can verify all this yourself. That's what's so good about flat earth science. You make a hypothesis, you test it, and you see. And I did not necessarily know what the output of my formula would be. But now I believe I have a more accurate formula than the Haversine. And you see how elegant the flat earth formula is. It's beautiful. Where with the Haversine formula, it's all a mess and it makes no sense. Let's go down to the bottom, what I was going to show you for the conclusion. We see that it is a highly accurate model. It provides a mathematically sound method of doing these calculations, most importantly on the Gleason flat earth map, and without having to do any spherical trigonometry. Now, we do 2 unique flat earth concepts here. Let me find citation 1. Citation 1 is that we realize we can't do just a basic Cartesian approximation. Why? Well, that's because we know that there is a fluid ether that exists within our universe, not a rigid ether. That's been disproven through many experiments like Michelson-Morley, and over time we learn that the idea of a solid ether can't exist, and what actually exists is a fluid ether that seems to actually drift at about 15 degrees an hour. So I think people like Bob Nodell many years ago actually calculated this, but at the limitations of flat earth science at the time, we didn't know what it was. Is it the globe rotating, or is it the ether? And these new knowledges really allow us to become more confident in our understanding of flat earth. So citation 1 is the Lorentz-Latitude hypothesis for the Gleason map. This explains how, as we travel latitudes through the ether, there is going to be an actual contraction. It's not that the Gleason map is wrong. If you're up that high looking down, it will appear like that, but as you physically get there, there is a length contraction. If you don't account for that, you'll never ever measure an accurate distance on flat Earth. Now, I wrote this September 8th. I didn't just make this up for this challenge. This is settled science that has been around for a while. Now, citation 2. What we then do is we realize that the effects of special relativity in the Lorentz ether transform depend on how high the celestial dome is. Now, what I realized is that my original number was wrong. You can see here, if you go back to May 8th, I originally argued, now this is in miles, I'm not going to try to misrepresent this 6,000 and claim that it's the same 6,000 that I'm claiming here. This is in miles. We're doing kilometers here. So this would be about 10,000 instead of 6, just so you see what I'm talking about. But what happened is I thought the height of the dome was about 6,000 miles. I'm now realizing, because I wasn't accounting for relativity back in that time. It's only now that we have a really good way to quantify this that I'm learning now that the dome is actually going to be that high up. And those citations are down here. So when you get this PDF to read, it's just at the bottom. Go through it, see it, ask me questions about it. But that's the fundamental concepts of the flat Earth distance formula. It's very, very powerful because we can look at the globe Haversine formula. Okay, see that they did try to simplify stuff in the flat Earth formula, solve for stuff, and simplify it down to spherical trig, and they're close. That's the thing. We can't pretend that the globe model can't make predictions. It can, because it's based on flat Earth. Anything the globe can do, flat Earth can also do. And I believe I did it better. So thank you for listening to my presentation. I am very proud to submit my challenge for the final experiment, and I hope I'm the first submission. This will be a great introduction to see what other flat earthers can come up with, and to also see if globers can come up with their own formula, or if they're just gonna repeat the Haversine formula. Thank you.
What is flat Earth science? Well, it's asking the questions other people are too afraid to ask. It's the willingness to face any challenge, knowing that failure is how we get better. It's about testing our hypotheses using first principle concepts.